Hello, class. This is Mr. Hart. And this podcast, we want to talk about how we calculate Doppler shift. Now, in class, we already talked about Doppler effect and what it is and how it works, but we never went into the details of the math of how we figure out how much a sound will change based on how fast you're moving. So that's what we want to do on this lesson. And so just to review quickly, let's talk about Doppler effect again and review what it means and how it works. So Doppler effect is the idea that as a sound source moves, the perceived frequency you will hear will go up or down based on whether it's moving away from you or towards you, because the wave peaks get closer together or further away from you as they travel towards you. Now, we're going to talk about mostly in the context of sound, but you can also think about it in terms of light and the color of light as well. And I've also put some videos on the website. There's a great example video showing the sound going down in frequency as a car is moving towards you, and then suddenly it moves away from you. You hear a sudden drop in the frequency. It's quite interesting to hear and listen to. Again, also, we've talked about before, this occurs because as a car, or whatever it may be, is playing a sound and is moving towards you, those wave peaks will be closer together, giving the perception that the sound is higher in pitch. Or as those wave peaks are going away from you, they will be further apart, giving the perception that they are lower, or that the sound is lower. But again, this is all great. The idea is relatively simple. But how much shift will there actually be? Now, there's a couple of things that actually affect this. One of these is the speed of the wave itself, like the speed of sound, how fast it's moving. The other is the speed of the object, of the source or the observer, how fast they are moving, or both of them together. And then also, obviously, the frequency you're listening to start will affect what frequency you hear in the end. So when we combine all these factors together, we get this equation. Okay. Now, there's a lot of stuff going on here, but let's just break it down. Okay. So, first of all, what we call f prime right here, this is the perceived frequency. Okay, the frequency you actually hear in a Doppler shift is equal to a whole bunch of stuff on this side, but first of all, it's affected by the speed of the sound wave or the light wave. Let's just focus on sound for now. The speed of sound plus the velocity of the observer. That is not velocity initial like we've seen in other cases, but the velocity of the observer over the speed of sound again plus the velocity of the source. And then all of that is times by the regular frequency that we were supposed to hear, or oftentimes what is called the emission frequency. Okay, what was the original frequency it was emitted at? Okay. Now, if you think about this, it's really quite a straightforward idea. The frequency that we are emitting is being changed by one ratio. There's a lot of stuff that affects that ratio, but it's just a single constant when all of that is simplified to give us our new perceived frequency. So after we simplify all of this stuff in this fraction, we just get our old frequency times by something to get our new frequency. And this ratio is affected by how fast the waves are moving and by how fast the object and the source are moving relative to each other. Okay. Another big thing, okay, this is really important. Okay, this assumes that the observer is on the left side of the source, and it also assumes that positive velocities are moving to the right. Okay. Once we get into the math, you'll see that the math is not that hard. The hardest thing is keeping track of if the velocities are positive or negative based on the scenario. Okay. So let's go ahead and do a sample problem, and I think you'll start to see how this works. So, problem 1. Okay, a car is moving at 18 meters per second as it is driving down the road. It honks its 520 hertz car horn at you to tell you to get out of the middle of the road. What is the frequency you hear as it approaches you? So if we are doing this problem, we say, well, first of all, we know our emission frequency, our original frequency, is 520 hertz. Okay. You are not moving as the observer, which is 0 meters per second. But then the question is the velocity of the source. Is it positive 18 meters per second or negative 18 meters per second? Well, if we draw the scenario, I'll draw it up here. We've got a little person, right? That's you. We're going to assume you're on the left, and so the car is on the right. Now the question is, here's our car. Because it's moving towards you, that must assume that it is moving to the left, towards you like this. Okay, so that means this must be a negative 18 meters per second, okay, based on how we draw the scenario to make the math work out. Okay, so if we do that, we get the frequency prime equals C plus V naught over C plus Vs, velocity of source, times the frequency. And in this case, that is 343 meters per second plus 0 over 343 meters per second minus 18 meters per second. All of that times 520 hertz. And so we just got to get that all in our calculator. Okay, just make sure you're keeping track of parentheses. You should get, when all is said and done, 548.8 hertz. Okay? So that's the new frequency you will hear as the car is coming towards you. Okay, and again, pretty simple. You just need to determine your velocities, put it in your calculator, and you're good to go. We just got to keep track of the signs. Okay, let's do another example. Okay, so same scenario. You then decide to run away from the car at around 4 meters per second. The car is still moving at 18 meters per second and honking its 520 hertz car horn. What frequency do you hear now? So if we're assuming that you're on the left again and the car is moving towards you, okay, then you also must be moving to the left because you're running away. So that means we'll have the same setup. Frequency is 520 hertz. Your observer velocity is minus 4 meters per second, and the velocity of the source is minus 18 meters per second. So plug it all in again. F prime equals C plus velocity observer, C plus velocity of the source, all times by F. That will give us 343 meters per second minus 4 meters per second over 343 meters per second minus 18 meters per second. All of that times by 520 hertz. Okay. Again, pull out the calculator. You should have 542.4 hertz. Now, this is a good time to do an intuition check to make sure that the number you're getting makes sense. Now, even though you're running away from the car, it's moving faster than you, which means you should hear a frequency that's higher than your original, right? So 542.4 hertz is higher than 520 hertz, so that means we probably did it right. Okay, let's do another one really quick. Okay, so the car runs you over in an unremorseful fashion. Again, it didn't slow down a bit and is still moving at 18 meters per second and honking at 520 hertz. What is the frequency you hear after it passes you? Okay, so now here's the car, still moving to the left. Here's you run over on the road. Okay, so if we're trying to write our values, we might say 520 hertz. Okay, velocity of the observer, you're just on the road, so that's 0 meters per second. You're not moving. But the question is, what is the velocity of the source? Is it positive 18 or negative 18? Okay. Well, again, our math always assumes that the observer is on the left, but in this scenario, the observer is on the right. So we need to flip our description here and think about it as you on the road on the left side and the car now being on the right, moving to the right. Okay, we got to kind of mirror our description here. And when we do that, we get that the car is now moving to the right with 18 meters per second, so our velocity is now positive. Okay? Now I'm just going to erase that to give us some room. So we have that our new perceived frequency is 343 meters per second plus 0 meters per second over 343 meters per second plus 18 meters per second, all times by 520 hertz. Okay, and when we plug that in one last time for this problem, we get 494 hertz. Okay, and again, we can do an intuition check right here to make sure that we're thinking, okay, the car is going away from you, so you should be hearing a lower sound wave, a lower frequency. Okay, so intuition checks off. We should be good. All right, so again, hopefully you can see that these problems are relatively straightforward, but they do require you to make sure you're visualizing them properly so you get the plus and minuses correct. Okay, let's do just 2 more examples. Okay. One thing to consider is that we can also do this for light. The only thing we have to change is if we're using the speed of sound, instead we will use the speed of light if it's a light problem. So in this problem, to us the sun appears to be a bright yellow, 5.20 times 10 to the 14th hertz. However, we are moving towards the Andromeda galaxy at 111,760 meters per second. If you lived in the Andromeda galaxy, what color would our sun appear to be? So again, let's draw this problem actually first. So we got our sun. There you go, right? That's what suns look like, right? And we got the Andromeda galaxy over here. But in reality, right, we always need to make sure we're putting the observer on the left. Okay, so I'm actually going to put Andromeda galaxy on the left, which I guess is just a circle, and the sun moving towards it like this. Okay, obviously not to scale. And so if we're writing down our values, we got frequency equals 5.20 times 10 to the 14th hertz. We got velocity of the observer. We're going to assume it's 0. It's not really, but in the setup we're going to assume it's 0. And the velocity of the source, you can see, is moving to the left, so this is negative 111,760 meters per second. Okay, so now if we put in our equation, f prime equals c plus v naught over c plus vs. Sorry, I keep saying v naught. It's really just velocity of the observer. And then we times that by the frequency. We can plug this all in, but remember, we're not using the speed of sound anymore. We have to use the speed of light, which is 3 times 10 to the 8th meters per second plus 0 over 3 times 10 to the 8th meters per second plus, or I should say minus, 111,760 meters per second. All of that times by our frequency, which is 5.20 times 10 to the 14th hertz. Okay, I'm sorry, I kind of ran out of space there. But if we put this all into our calculator, just like we did before, our final answer is that the new color is 5.202 times 10 to the 14th hertz. Okay, so that, even though we're moving pretty dang fast towards that galaxy, it really doesn't shift the color that much compared to the speed of light. Okay, let's do one more problem just for fun, one of the classics in physics. Okay, let's say you're driving down the road and speed through a red light. The cop pulls you over, and in order to not get a ticket, you claim that you actually saw the light to be green because of Doppler shift. Okay, because you're a good physics student, so you say, oh yeah, that's obviously something that could happen, which it can. But the question is, how fast must you have been driving in order for this to be true? Well, first of all, notice here that we actually have the two frequencies, so we have to change the problem a little bit. Okay, so we start with f prime equals c plus velocity of observer plus c, or over c plus velocity of source times f. We actually need to solve this for the velocity of the observer. And in this case, there is no velocity of source because the light isn't moving, the stoplight isn't moving. Okay, so we need to solve this whole thing for velocity of observer. So if we do so, we get f prime over f equals c plus velocity of observer over c. Next, we can times by c, so we get f prime over f times c equals c plus velocity of observer. And then last of all, we minus c over, so we get f prime over f c minus c equal velocity of observer. Okay, so I'm just going to write this up here so we have more space. Now we know our two frequencies here. Frequency prime equals 5.86. That's what we're going to claim we saw. And our original frequency of red light is 4.50 times 10 to the 14th hertz. So if we plug it into this equation up here, we just basically get the division of those two. F prime over f. That times by our speed of light, which is again 3 times 10 to the 8th meters per second. And minus the speed of light again, which is 3 times 10 to the 8th meters per second. All of that should give us our velocity of the observer. And when we do that, put it in our calculator, you should get that your new velocity is about 9.1 or so times 10 to the 7th meters per second. Okay, so that's about 90 billion meters per second is what's required to be seeing that light as green. So pretty fast. You have a much bigger speeding problem than a running the red light problem if you actually see that as green. But anyway, it's just a really fun problem to think about, and also think about how you can manipulate these equations as needed to solve what you're looking for. But anyways, that's pretty much it for Doppler shift. Go ahead and do the assignment connected with this lesson. Let me know if you have any questions, and thank you for watching.